Thank you. This is joint work with Dean Eccles, and we're talking about bootstrapping tensor data. Just to calibrate for a beginning point, we'll talk about what does the bootstrap look like in the IID setting. And the bootstrap is this enormous labor-saving device. Instead of having to do all the math to figure out the variance of your statistic, you just do a Monte Carlo. And what you do is you sample your data as if it was the distribution, calculate your statistic a bunch of times, and the variance of that histogram that you get is a good proxy for the variance of your original statistic. So statisticians love this because at face value it just makes sense. You can explain it to a scientist, they'll believe it. There's a lot of deep theory if you wanted to figure out how to bootstrap X bar. Now we kind of know how to handle X bar, but the reason X bar is so important, the sample mean, it's so important because if you can get that, then you can get smooth functions of the mean. So you can get correlations and variances and regressions. You can also get maximum likelihood estimates. So basically, if you get X bar right, you get any finite dimensional parameter right. So that's why X bar is the sweet spot to study, and that's why we love the bootstrap. And it's valid under really mild conditions, just IID samples and a few finite moments. Okay, so here's how IID data vectors work. We have cases and variables. So usually you get your data, you throw it into a matrix. The rows are just these anonymous variables, and the columns have names. So the columns might be temperature, pressure, income, and whatever. The rows actually are anonymous. We don't really care about them. Row 42 doesn't mean anything to you. Row 42 in the next data set has nothing to do with row 42 in this data set. So actually we don't really want to know about the rows. We just want to know the joint distribution of the column variables. That's in the IID world. A lot of data that people get now is quite different, two-way data. So think of the Netflix data. Now a given row, that's a movie. That's not an anonymous thing we want to throw away. We actually want to understand that movie and recommend it to some of the customers. The columns aren't anonymous either. Those are customers who want to figure out what they want to watch. So this is two-way data. It's all interlocked and tangled, and it's not appropriate to model it with IID samples. And there's lots of examples. So on the bottom of the slide, genes and environments, terms and documents, lots of rating data. There's a lot of data that has this form where it's entities by entities. So the rows and columns are both entities, and neither is anonymous. And it can be easily more than two entities. So imagine that you talk to your friends at Amazon, and some customer U comes in from a machine with IP address M, they enter a query, they look at a review, they buy a book, they use a credit card, and so forth, and you get a tuple, maybe 5, 6, 7 of these entities are attached to like every dollar value or every unit count or timestamp or something. So you can easily get to more than 2 dimensions, although 2 is the usual. Okay. We can, in fact, rearrange this data to be just anonymous rows. What we could do is we could turn it into tuples. So case 1, it's got this movie, that viewer, and such a rating. Okay, so now the cases are anonymous, except the rows aren't independent anymore. If you look carefully, the first 2 rows, it's about the same movie. So if that's a really good movie or a really bad movie, it's going to make the ratings correlated because the ratings of the same movie, not independent. If you look at case 1 and 3, it's actually the same person. They're not independent either. So there's a real tangled mess of correlations amongst your data points. You can't just bootstrap naively. And why would we want to bootstrap? If I have 100 million movies, maybe I just know the answer to everything. Well, it turns out even in a large data set, you still have some uncertainty left, and bootstrap would be a nice way to measure it. Statisticians have been looking at these kind of two-way models for coming up on a century now. And the simplest possible example is a random effects. So we'll suppose that you just have this matrix and you add a random number to every row. Then you add a random number to every column. Then you add independent random numbers. And that would get you a random effects model. Now suppose that you just wanted to know the underlying mean. Again, we want to know more, but if you get the mean right, you do get more. Well, it turns out that you can't actually bootstrap that problem. And in a quite unusual and very interesting paper, Peter Mc-Cullagh proved it's not just that nobody figured out how to bootstrap it. There does not exist a bootstrap for that problem. So it's out of bounds. You or I or Chuck Norris, nobody's going to bootstrap that random effects model because it doesn't exist. So what about classic approaches? I mentioned these things have been going on for almost a century. So there are classical approaches to random effects models. They get kind of messy when they're unbalanced. And the Netflix data, well, that's like 100 million. That's not big data. Unless you're dealing with n cubed, then suddenly it feels big. You don't want to do anything n cubed on the Netflix data. And the solutions for in agriculture, where it's cows and bulls and how much milk and all that, those are done on small samples where you could do the linear algebra. For something big, you really want to do, you don't want to do the linear algebra. You want to do some kind of bootstrap. Okay, so there is some good news. There's an approximate bootstrap that would work. So let's look first at this very simple column. We have a completely regular grid, R rows and C columns, and we just want the average. So one thing you could do is ignore the structure of the data and just bootstrap those n values. Okay. Or the other thing you could do, and the thing that we like, is you could bootstrap the rows and then independently bootstrap the columns. So suppose your favorite data point is row 1, column 1. And I do a bootstrap, and row 1 comes in 2 times in the bootstrap resampling. And column 1 comes in 3 times. Then your favorite observation just came in 6 times as a little 2 by 3 matrix. So that's what this bootstrap 2, this product resampling, would do. Operationally, you're taking every row and multiplying it by a weight, every column by a weight, and every data point by the product of those weights. Okay. In this simple setting, you can work out what the variance should be. So if it's really Gaussian and everything, you wouldn't do a bootstrap on this case. And we know what the answer is. If you do this naive bootstrap, you miss it by a mile. Okay, so the real variance is row variance over number of rows, column variance over number of columns, error variance over the product. If you do the naive bootstrap, you're putting everything over the product. So if you think of R and C as 1,000, instead of having this one over 1,000, the next one over 1,000, and the last one over 1,000,000, you have everything over 1,000,000. You just underestimated your variance by a factor of 1,000, so you'll make unreliable conclusions. What about this product bootstrap? Well, you get the rows over 1,000, the columns over 1,000, and the error, instead of getting error over 1,000,000, you get 3 times the error over 1,000,000. So you tripled it. That's not so bad, though, because the thing that you tripled is probably way smaller than the dominant terms, and also you've bumped the variance up a smidgen. So your conclusions will at least be reliable. They may be a touch too conservative, but they're at least reliable. So that's the method that we want to generalize. In the case of R equals 2, I have an older paper where I worked this out, and this product bootstrap, it allows for missing data. Like the Netflix data is 99% missing. That's not really a serious problem. And you could have every movie have its own different variance, and every customer have their own different variance. And indeed, the customers in that data set are quite different from each other. Some of them just give 1s, some of them give 1s and 5s, some of them give 3s and 4s. Okay. If you do the naive data, you can show that the naive bootstrap will underestimate the Netflix variance by potentially a 50,000-fold or more. So it would be really bad luck if you present a variance and you're under by 50,000. Okay. And in particular, if you scrutinize the Netflix data, the ratings made on Tuesday are the lowest ratings of any day of the week, and people are the most generous on Sunday. But it's a smidgen difference, 0.02 stars. And if you're off by 50,000, you might not be able to get the variance of that 0.02 star thing right. But using a reliable variance, you see that it is a real difference. Maybe it's not important enough to make money off of it, but it is a real difference. Okay, so for the work I want to show you today, there are a few goals. What happens to that 3? Like if I go to a tensor data with three types of entities, what happens to that little red 3 of my conservatism? Well, it goes to 7. In general, it goes to 2 to the r minus 1. So if you have a 4-way tensor, you're 15 times as conservative on the very highest level interaction. But you're never underestimating. What if there's missing data? Missing data is not a problem. What if missingness is informative? Okay, maybe it's really informative which movie somebody rates. Well, of course it's informative. You can't bootstrap your way out of that problem, though. You'd have to model your way out of that problem. So that's like off the table for today. If the entities have an unequal variances, that's not a problem. If we want a little bit more than x bar, like maybe I want y bar divided by x bar, or maybe I want x1 bar minus x2 bar, those kind of things are not a problem. If I want a lot more than x bar, I don't have it today. So what would be a lot more than x bar? Maybe I want the leading eigenvector of some matrix. Okay, I would love to bootstrap that leading eigenvector. The theory that I'm showing you today doesn't show how to do that. It's pretty clear that the naive bootstrap can't do that because it can't get x bar. So if any bootstrap has a chance, maybe the product bootstrap does. Okay, so the data sets that we looked at, there's the Netflix data. This is a pointer? Okay, awesome. Okay, so the Netflix data you're familiar with. There's 100 million ratings and 500,000 customers, and they get 1 to 5 stars. I'll show you the 3-way data we used, courtesy of Facebook. It's sharing data. So here's an example. So Alice shares a URL, and so Alice says, "Hey, check out this URL." Okay, and Bob is the commenter. Bob's very enthusiastic. Bob says, "Thanks for sharing that. I learned a lot." And then the data set that we get have these 3 entities: which URL it is, the Alice who shared it, and Bob who made the comment. Okay, then what do we record? We record how long was the comment, the log number of characters. Why do we record that? Because it doesn't give away any privacy, and because Facebook isn't interested in that statistic. They're probably interested in whether somebody clicks or likes something that makes money or enhances the user experience at Facebook, but they wouldn't really want to publish that kind of data. So this is like a harmless statistic to quote, and we'll look at how long are the comments that people make in the US, and we'll compare it to the comments that people make in the UK. And who talks more, US or UK? That would be, there'd be some social interest in that, and it doesn't give away any of Facebook's crown jewels to talk about that sort of thing. Okay, so the random effects model works as follows. We take an index and say there's R different kinds of entities, like URL, who shared, who commented. But in general, there could just be R of these entities. And one of those entities, well, they're just a natural number. So there's basically an infinite number of friends out there, you haven't met them all, or an infinite number of URLs and you haven't seen them all. We might as well not stick a bound on it. So we're just indexed by the natural numbers. And we have to deal with sub-indices, so maybe just the URL and who commented. Okay, so we take a subset of those indices. And then the data are real valued. We'll just use scalars. Okay, so the model has this countably infinite set of data. And of course, we don't get to see it all. We only see the ones where zi is 1. So zi is 1 if we saw it, 0 if we didn't. But we'll model all the data that we didn't see anyway. And the model is that there's some grand mean. And then for every observation and every subset of its entities, there's a little random effect that has mean 0 and variance sigma squared. And if 2 data points had the same set of entities, if you take the same set of entities and the same exact entities, then there's a covariance of sigma squared. Otherwise, it's 0. Okay, so that's what you get from this random effects model. So there's, say, in Netflix, you add a random effect for every movie, you add a random effect for every customer, you add a random effect for every movie customer pair. If there were movie credit card pairs, you'd add a random effect for that, and so on. Okay, so it's a bigger model than we might need. In the simplest case, we just say that the variance, say the variance for movies and customers might be the same whatever movie customer pair. In general, we can actually allow every movie customer pair to have its own variance. Okay, so here's how the reweighting bootstrap works. We're going to calculate our average, and here's all of the x's in the universe, but we just count the ones that we measured with z equal 1. And then we divide by the sum of the z's, which is our sample size. So we do need to assume that at least one observation got made. Okay, so there's a mean. And if we reweight the data, all we do is we put a weight in between the presence indicator and the x, and we put a weight in the denominator too. So now we estimate the population mean by a weighted mean. Oh, sorry, there's a sample mean, and there's a bootstrap sample mean. And what's going to be our weights? These will be random weights, and we'll multiply up weights. We'll multiply, like say, a weight for the movie, a weight for the credit card, a weight for the sharer, a weight for the URL. We just multiply them all in. And these weights have the property that their mean is 1 and their variance is usually 1. It's easiest to have the mean 1, variance 1. Okay, so that's our product reweighted bootstrap. So the usual bootstrap, you can think of it as weighting 2. We just put these multinomial weights. So in the usual bootstrap, how many times does observation 1 come in? Well, it comes in almost a Poisson number. It comes in a binomial number of times, but they're geared to add up to exactly n. Rubin published a Bayesian bootstrap where he replaced these weights by exponential random variables. The exponential distribution with mean 1 also has variance 1, and so it works. Popular in some machine learning applications is to replace the bootstrap by IID Poisson weights. The sweet point about using IID weights is that your data may be scattered over servers all across the country and the world. You don't really want to make sure that the weights always add up to 100 million. You might just as well take them independent Poissons. They'll come out close to 100 million anyway, just by the law of large numbers. So that's a huge simplification. And another approach is to just do half sampling. You toss a coin. If it's heads, the data point gets weight 2. If it's tails, the data point gets weight 0. And pretty much anything you can do with the bootstrap, you could just do by this double or nothing trick. The same justification theorems will go through. This is actually the one that we like the best. So why do we like half sampling? Well, look at what happens to your weight. It's a product of zeros or twos. So everybody that gets a non-zero weight must have got all twos. So they must have had twos all the time. And that means that they're all getting integer weights. It's a nuisance for some algorithms to put weight, pi over 7 on a data point. Who wants to do that? I'd rather, if I put weight 3 on a data point, I can just put 3 copies in. Much easier. Many more algorithms can handle integer weights. In fact, all of the non-zero weights are equal to each other. So you don't even have to mess around with copies. You just select out the ones that got non-zero weight and do your calculation on them. And the other thing is this distribution, which has equal weight on 0 and 2, that has the smallest kurtosis you could have, subject to having mean 1, variance 1. So it's actually statistically the most reliable way to go. Okay, so now we have to figure out, does this reweighting bootstrap actually work? So we need to think of what's the true variance that we would be trying to estimate. So if the observations are generated this way, a grand mean plus all of this ocean of random effects, and those random effects have their own variance for each subset, well, here's our estimate. It's just this weighted sum of the data points. So the variance, just take 1 over n squared, take a double sum, and now it's a covariance. And I had a covariance formula. First of all, zi and zi prime means observations I and I prime are both in the data observations that are not in the data don't contribute to the variance. Things only contribute if they share the same set of entities, and then they contribute whatever the variance is for that entity subset. Okay. So when the dust settles, it's just a linear combination of the variances, say variance for sharer, variance for URL, variance for commenter, sharer, interaction. So in the Facebook example, there's only 7 different variances, and it's a linear combination of those 7 with these magic constants, gain coefficients nu. And so this is sort of an unwieldy formula, but you can compute it on any data set. And here's how it looks like for the Netflix data. For the Netflix data, if the movies have a variance, then the average has 50,000 times that movie variance over n. Not 1 over n, 56,000 over n. And there it is for viewers and interactions. What's the meaning of that 56,000? Well, this is 100 million. There aren't 100 million movies in that data set. So there's no way that you should get a variance of 1 over 100 million for something that depends on movies. What do you get? Well, you get 50,000 over 100 million. That's basically 1 over 2,000. So the Netflix data has the moral equivalent of 2,000 independent movies. It's not tiny, but it's not 100 million. And for Facebook, we get similar. In particular, the URL has a huge component. So you can't treat that like independent. Okay, if you sample naively, you want this gain factor nu, say 50,000, and what you get is basically 1. Okay, so naive bootstrap is excruciatingly wrong for this kind of data. What about the product bootstrap? Well, the product bootstrap has this random numerator and denominator. We will use a ratio, it's a ratio estimator, and there's a standard formula for variance of a ratio. Cutting to the chase, the variance that we get will also be a linear combination of all these variance components, but instead of getting the desired variance nu, we'll get something else, gamma. And the big deal is that the gamma we get is pretty close to nu for main effects, like one entity at a time, and otherwise it's a small multiple, but it's bigger than 1. Bigger than 1 is the side that we want to be on. We don't want to underestimate the variance and then have to retract a claim later. And the fact that it's only a little bit bigger than 1, like it might be 3 times bigger than 1 instead of being 50,000 times smaller. Okay. Okay, there's an exact formula which captures some extreme cases that we don't really want to worry about. Like if half of your data was from one movie, the variance formula that I showed would actually capture that, but that's not really relevant to most data sets. So we don't usually have that much level duplication. There's also a phenomenon of variable duplication. If 2 people have the same, 2 entities or 2 data points have the same name and phone number, they probably have the same fax number. If they have the same age and zip code, they probably don't have the same occupation. So the relations among these entities are quite different. Sometimes it's almost like an independent shot, and sometimes it's pretty dependent. That will make a difference to the variance formula captures those effects from the data. Okay. So I'll illustrate these with an example. If you look carefully at the Netflix data, 1/5 of 1% of the Netflix data is people rating miscongeniality. Okay. Okay, you gotta love Michael Caine, but anyway, so 1/500th of the data set is people rating miscongeniality. That's this quantity epsilon. For the Facebook data, almost 4% of it came from one of the URLs. And the level duplication thing, these are, this was small for Netflix, not small for Facebook. That means that our formula will prove to be a little bit too conservative for Facebook, but accurate for Netflix. Okay, here's what we proved. There's the variance you want. There's the variance you get. It's 2 to the cardinality minus 1. This is the duplication thing, like 0.0002 for Netflix. So basically just look at 2 to the mu minus 1, and then things rain down from the higher order interactions. But if those duplication indices are both small, then the multiplier you get is the multiplier you want times a small integer. Okay, and the 3 turns into a 7. Okay, I'll skip these. They're best read in the comfort of your own office. Now let's look at the Facebook data. So in the Facebook data, we broke it down by whether it was US or UK. We also looked at whether it was made on the web or made on a mobile device. And here's what we found. On the web, on mobile devices, the people in the UK actually make longer comments than the people in the US. If you look on their web forums, the people in the US are actually more loquacious than the people in the UK. Okay. These are actually pretty small differences, but they're statistically significant. And here are we bootstrapped the empirical CDF, or was it empirical CDF under bootstrapping of this quantity. If you just bootstrap the commenter, you get this very narrow distribution, and that's not accurate. If you bootstrap 2 of the indices, you get this. You bootstrap all 3 of them, then you can capture the real uncertainty. It's this empirical CDF, but it still doesn't go, well, I'll tell you what this axis is. This is mean characters for the US minus the UK. So it's negative because the US comments were shorter. But it goes from, say, negative 0.12 to negative 0.05, so it's always negative. So that means the sign is at least determined. And here are confidence intervals. They don't overlap 0. And taking account of all the uncertainties, you get wider confidence intervals, but wider ones that you can now trust. I'm going to skip, maybe I'll, okay, so what's happening here is every individual person-movie combination has its own specific variance. As long as those are bounded above and below, then we can still do this bootstrap. You don't have to estimate all of those. There's more variances than there are data points that you'll ever get. Okay, where might that come from? You can generalize a factor model. Usual factor model, you have something for the row, something for the column. You could generalize it to be some fixed thing about an arbitrary subset of variables and a random thing about the complementary subset. And that would get you into that model that I showed you. Okay, so a few gaps and things to do next. This resampling method does not imitate the way the data were generated. Usually the bootstrap is just imitating how you got your data. This one doesn't. It still remains to handle informative missing data. It would be interesting to estimate those variance components. I believe it may be possible to do this with bootstrap of b equals 1 time. A unistrap may be possible on this data set. You might only need to do it once. I'm also interested in what happens to the row means and column means, whether you can, this might be a measure of how good is movie 45, or how good is like the latest Harry Potter movie. You may want a confidence interval on it alone, or a difference of 2 movies, or the whole movie vector. That would be something to do next. Okay, so in concluding, I want to thank Dean Eccles, my co-author. I want to thank companies. Anytime a company lets data out, they should be thanked. I want to thank Michael and the other organizers and acknowledge my NSF support. Thank you.
So, if not, I have one question. So does this, does this apply also to, sometimes we would like to get more like robust estimate of some of the quantities like medium, or
yes.
Does this also generalize to different type of statistics we like to collect from the data?
It will generalize to quite a few different types. Like, for example, you could take a Huber estimator. So the Huber estimator just says the mean of some quantity equals 0. And so you can relate it back to a mean and then apply this method. So yeah, if you can get the mean right, then you can get implicit functions of the mean and get lots of other things.